Log on, tune in, find out. Another good idea from Cambridge.
A brief outline of my talk. So actually, I think a more appropriate title for this talk would have been A Mathematician's Approach to Network Coding, because it takes more than 30 minutes really to get into sort of the logical aspect. But still, I hope I'll be able to say something in the end. Also, this talk is really just a brief taster, and I really try to keep it simple. I think these days it's almost called outreach or something. You know, you have to. So I mean, it's really don't get insulted if you think it's a bit too slow. I mean, but basically, I think it's more. I just want to give sort of some very basic ideas, and then explain how it's related to some very deep and interesting questions. Because it's an introductory talk, some of the material I have used before at various types, but I mean, I will talk about things today that is completely new. But you will see some of. I don't think any of you have seen it before. I don't know, but there will be some pictures I have used from in other presentations, because it's all the same kind of story. So network coding is a quite young research field from 2000. So far it has mainly been a research field in electrical engineering. So it's it's a field that contains many interesting problems. It's a very interesting, rich area for a mathematician. So let me explain a bit about what it is. So in internet communication, or in general in communication networks, there is, like you can say, usually data is treated like packages. It's packet switching is of course central, and on many different levels messages are being sent and split into packages, and so data is in some sense treated like an ordinary commodity, like simply a thing you send from A to B. However, in network coding, this network coding challenge this kind of way of looking at data. So here's a very basic example, sort of, you can say an example that started the field. Actually, many of these things in network coding, many of these ideas were known long time before, certainly in circuit complexity. A lot of these ideas were known already in the 70s, but I would say that it was first in network coding that people studied these problems as something that could potentially be applied also. So here's an example. So suppose we have like two base stations on Earth, and they want to communicate via some satellite. Let's say it could be a stream of messages, or maybe we can just say one message X selected from some message space, and we want to send that message from east to west. And at the same time, we also have a message Y we want to send from west to east. So normally in traditional framework, what would happen is that the two base stations, they beam up the signals to the satellite, and then the satellite will basically beam back to Earth the two different messages, maybe on two different frequencies or for different times. But the idea in network coding is that it simply beam back a function of the two messages. You get the two signals, and then from these two signals, you combine the signals and beam back another message. So let's see. I knew that. Let's see. Here we are. Yeah. So, for example, so if the satellite beam back a message which is a combination of the two messages it received, let's call this for f of x, y. That's like the combined message. Then you can see that that east. Let's see. Go back here. East, I think. Well, east. One of the east know, of course, its own message, and it also knows the message it receives, and it requires message Y. And vice versa, west knows, of course, its own message, but it also knows the message it wants to receive, and it knows what to call it. It knows f of x, y. So, as a simple mathematical question, we can ask what kind of functions can be used as coding functions here. And of course, probably you noticed that one choice, if we just have two messages, 0 and 1, we could simply choose the exclusive OR of the two messages. Then it becomes, the whole thing actually becomes pretty trivial, because what is happening here is that you can say that one station is sending us a stream of zeros and ones up to the satellite, and the other ground station also sending a stream of zeros and ones, and the satellite simply just take the exclusive OR of these two data streams and beam them back to Earth. And then, of course, each of the two stations can reconstruct the other message. Okay? But you see, the requirement for such a coding function is exactly that it's a Latin, defines a Latin square in this way. It means that, for example, if you're sending 2 bits up, if you have an alphabet of size 4, you can see we have like a Latin square here. Each row and each column contains different elements. So if you really want to do outreach, to these days, then you can say that it's like a Sudoku problem. You can basically use Sudoku to solve satellite communication. So here is the same kind of another representation of the same problem. We have two messages, let's say x and y, and we want to send them to some receiver nodes. And f of x comma y is again this combination function and or encoding function. And then we can again see that it's the same requirements as before. If f defines a Latin square, that's exactly a requirement for the communication to be successful, so the requirement can be satisfied. So here's another simple idea for network coding. Suppose we want to sort of to storage, let's say, two messages x and y, and we want to store them in 4 locations. So let's, for simplicity, say that 2 of the messages are already stored in the two first message locations. So we have x and y stored up here, but then we want to store some combination, a message here, f of x comma y, which is a combination of the two messages, and it's the same for, we want to store some combination of the two messages here. And we want to do it in such a way that whatever 2 locations we access, we should be able to deduce both message x and y. So again, this is a simple example. If you only had, if you didn't have this node, it would actually be the same as a satellite problem, really. It's the same requirement we would have. But now, because we have both f and g, so we can see that we have f has to be a Latin square. G also have to define a Latin square. But because also from knowing both f of x comma y and g of x comma y, we need to be able to deduce x and y. So that means that we actually, the requirement is exactly that f and g defines 2 orthogonal Latin squares. So if you want to see how this look like, so if f and g, they are coding functions that solve this storage problem, if and only if they define 2 orthogonal Latin squares. That's the requirement. Here's an example of, you see for alphabet of size 4. So you can say that the main concern of network coding is this observation that digital information is not really an ordinary commodity, because unlike ordinary commodities like fruits and tomatoes or whatever you send, they were normally, the way they are being distributed is like items that then are being sent to some, say, supermarket or some storage space, and then from there they're being distributed further to the receivers. But of course, if goods could actually be copied during distribution, for example, clearly we would distribute it in a quite different way. It's a quite an important property. And digital information actually can be copied during distribution. And also it can be transformed, like we saw with the satellite problem. You can transform digital information. So basically, the question of how this copying and transformation can be utilized, that's the main concern of network coding. So now I will go to something that at first looks somewhat different, but it turns out that this is very, very closely related to network coding. And actually, from a mathematical point of view, it's more or less many types of problems in network coding can be restated in this form. But this is something that almost looked like a recreational problem at first. but it goes straight to the heart of network coding. So imagine we play a simple dice game. So we have like n players. Let's say n is 100, for example, and each of those 100 people, they have like a dice with s sides. So we could say s is well, I suppose is 6. So each player have a dice, and then in this game, the idea is that everybody rolls their own dice. Okay, but now you can only see. Imagine that each player can only see all the other dice values. They don't have access to their own value for some reason. So and the task is for the group. It's a cooperative game, but the task is that the whole group each individual have to guess correctly their own value, their own dice value. So, and the group wins basically. They win a big prize. If all of the 100 players guess it correctly, then they win a prize. Otherwise, they don't win anything. So they have to somehow see what's the best way to ensure that all of them guess correctly. And there's no tricks here. They're not allowed to communicate or anything. They just produce some kind of. They're allowed to agree on a protocol in advance. The day before, they can agree some kind of function they choose or some protocol. But then after that, there's nothing, no information, no communication or anything like that. And they all have to guess simultaneously. So what's the probability that each of the players guess correctly their own dice? I mean, not each individual, but the whole group guess correctly. Well, a naive and wrong answer would be that basically since each player has no relevant information about their own value, you remember each player is trying to guess their own value, but they see only all the other values. So because each player doesn't have any relevant information about their own value, it's sort of a naive approach to say basically it must be 1 divided by s to the power n, the probability that all of them get it right. I mean, in the example with n equals 100, you know, it's simply it's a very small probability that all 100 players guess correctly. That would sort of be the naive approach, but it turns out that is a serious mistake, that argument. So let's again check it, because it's kind of interesting to see where it goes wrong. So it is correct that each player has absolutely no relevant information about their own dice value. It's also correct that each player have a probability 1 divided by s of getting their own value. I mean, in the case of a normal dice, it would be a 6. That's exactly the probability that each player will guess their own value. That cannot be changed. And also each throw is independent. There's no dependencies here. But it's a big mistake to think that the probability that all players are correct is 1 divided by s to the power n. So if you wanted sort of the concrete numbers, you can see for the naive strategy gives a probability of a 6 to the 100. That's this very small number you have up there, 1 divided by this huge number. That's obviously very, very small probability, but it turns out that there's a strategy where they can achieve it with probability 1/6. They can do much better than random guessing. It's actually a very simple strategy, but the idea is they can basically bootstrap the success such that basically any player is correct if and only if any individual player is correct if and only if all of them are correct. So here is one such strategy where the players succeed. They agree simply on the following protocol. So each player assume that the sum of all the dice values is 0 mod s or 0 mod 6. So this is something they agree. I mean, they assume it. It might of course not happen, but they simply guess as if the sum of all the dice values could be divided by 6. And then you can see what happens is that if it actually happens that the sum is divisible by 6, that happens every 6 times. If that happens, then every single person gets their own value correct. So you see this strategy succeeds for the group with probability 1 divided by s. And that's much better than, of course, uncoordinated random guessing. So they basically, the player, so actually it's not hard to show that that is optimal. They cannot do better than 1 divided by s, 1 divided by 6. They cannot do better than that because that's the probability each individual is actually correct. But the point is that they can organize it in such a way that basically there is an incredible big correlation between how they guess, how if they're correct or not. So there's perfect correlation, so to speak, between when they're right or wrong, the whole group. So this is what on this slide. So basically by cooperating, they can kind of bootstrap their success by creating this kind of strong correlation between when they succeed. But now comes interesting. I will not go into details about the links to network coding, but what I will say is that you can play the same game on a graph, and it turns out you can also play it on a much larger class of more logical games. And basically what you do is that you take a directed graph and then you play it exactly like before, but now each player can only see all the incoming edges to you. So you can imagine each node represent a player, and so maybe you could go to some graphs here. So maybe we have a graph like this one. That means they're sitting sort of around you can imagine we have like in this case I think 12 players sitting around a table, and everybody can just see the dice values to the person to the right of them, and then you can play the same game. But you can also play it, of course, on many other types of graphs. And it turns out again, the property of the graph, there's a very close relationship between how well the players can do in that guessing game and how well the graph can serve as a communication network. Actually, there's a perfect relation by this theorem I proved quite a number of years ago. So I'm not go into big details with the argument, but the idea is basically that if you have, if you take a communication network where you have like say k players and they have k friends, so they want to send, each of the k players want to send a message to the friend. They're sort of paired up in pairs, you know. So have k input-output pairs if you want, and you have an acyclic graph, and this is like the communication problem. And so we want to see, can this be solved, this problem? So here we have the simple butterfly network from before, for example, but it could also be some other graphs. Now, if you take that communication network, take each of the k inputs and each of the k outputs, and now glue, so to speak, take each pair, so you take each node and its corresponding target node and glue them together, then you get a new graph. And this becomes a directed graph. The first one was acyclic, but if you glue each person together with his friends, so to speak, then you get a directed graph, and it turns out that there is a perfect relationship between the player's ability to play this guessing game on that graph and the solvability of the original network coding problem. That's all I will say for now. I'm not going to details with this, but I just say this is a result. So it's on the slide, so if you're interested, you can study the slide more carefully. But here's an example of how it works. So you see to the left, you see graph A. That's an example of a like a guessing game, if you want. But now here we're doing the opposite process. We take some of these nodes, in this case 3 of the nodes, and we split them. That means that we split them into 2 parts, each of the nodes, and then all the incoming edges goes into one of the nodes, and all the outcoming one goes into the other one. So you see you get like an acyclic graph like this. So the guessing game here is, it turns out that the number of solutions of this guessing game that achieve guessing number 3, I haven't defined that, but I mean they can basically do a factor s to the 3 better than if they just did random guessing. In that guessing game, the number of ways they can do that is exactly the same number of solutions you have, coding solutions you have to this problem. There's a very direct relationship. And this kind of trick can also explain why you can have a network that looks quite different. For example, the one in B and C are definitely non-isomorphic. But the point is, if you glue them together again, if you glue each sender together with the receiver of that message, if you glue them together, you get back to this original network here. That explains why the number of solutions and also whether the network has a solution or not, and all this is the same for these different types of networks, because they're really part of the underlying reality behind the networks is, so to speak, captured by the guessing game. So this is what we have here. So up to this point, basically, I just gave a brief introduction to this area. And since then, of course, a lot of things have happened, and it has been more technical, and I have supervised two PhD theses on this result, and I'm also sort of 1.5 years into an EPSERG grant on this. So obviously it has become, there are many more things I haven't told you about. And also there have been a spin-off in the form of a lot of different types of papers in different areas. So some of these areas are quite interesting. One area, for example, generalized matroid theory, and I'm not going into all of these areas, just to give you an idea that a lot of things has happened. But there is sort of a new development in a different direction, where you go into more into logic. So here's like you can say a sample question. This is a very general type of question that you can say sort of a logician's perspective of these things. And this type of question is so general that it easily captures all the other guessing games, and it captures a lot of other types of games. So suppose we fix a first order language and we take a formula in that language in n variables. And actually in this setting, I'm talking about finite models, so maybe one can also generalize to infinite models, but I'm just looking at the case of finite models. So we fix some formula phi in this language with n variables, and then we're also given a size of the model. And a task is to find a model of that size such that maximizes the set of tuples, such that the formula holds for these tuples. So as I said, this type of question is really very broad. In some sense you can say it's too broad, but the point is that it actually sort of captures, for specific choices of phi, it leads to interesting type of questions. And you can capture many types of problems. I mean, these guessing games can easily be captured even by a quantifier-free formula. For example, where you just have a disjunction of some simple terms, then you're trying to maximize the number of such tuples. That's the same as maximizing the probability that all the players are correct in this guessing game. So this can easily be captured even by a quantifier-free formula. You can also define some other guessing games. You might, for example, also have games where each player have a dice value, say, in the graph, but then somebody in general, an oracle or some general public channel, communicate to everybody some general information, and then we want everybody to be able to work out their own value. So, for example, with the example with the dice, when you have n, the complete graph, bidirected graph with n people, each player can have access to all the other values. All you need in order to tell them, to tell everybody what value they have themselves, is just to tell what is the sum of all the dice values, mod 6 and mod s. Then everybody can work out what their own value is. If you can see all the other values, you can work it out from that. So you can see that, but there are many other types of, you can also have some kind of hat puzzles where there is a delay, so some people they guess, but some other people they guess based on some other people's guesses. So these are sort of recreational puzzles you find, and these can be captured by these formulas also. Also problems in network coding, but also more interesting maybe from more applied perspectives, also a type of network coding where you have dynamic network coding, where you might have link failures and you might have other things. So let me just finish with some kind of you can say an application of the logical approach. So it turns out that for a very specific type of quantifier-free formula, just basically you just defined as a very simple form of basically some term sets T1 equals S1 and a conjunction basically of basic term equations. It turns out that captures, that's a very rich already type of model where you can model say what is called many-to-many cast networks. That means that you have n inputs, n senders and n receivers, and all the receivers, in this case in the many-to-many casting, all the receivers want the same message. All of them want to be updated. That's a bit like Facebook or something like that. You know that all of the users, all the servers for Facebook, they want to be updated with the same information. And it turns out that under very general circumstances, you can have changes, dynamic change of the network, a link fail, and a lot of other things. You can use this abstract model to show that each demand can be satisfied in isolation. So suppose it's a Facebook, so the first server of Facebook can be happy, all the other ones we don't care about. If there is a way we can, so to speak, set up the communication so the first server are happy if it just disregard all the other ones, and we can do, if we can, so to speak, satisfy each of the servers in separation, then you can prove that it's possible to satisfy all the demands simultaneously. And this is this results. This is basically the end of my talk. Thank you.
Any questions, comments?
Yes.
The terminology that you use suggests that there are applications in real world. Can you mention something about?
Well, I mean, there are applications in network coding, but I think it would be a stretch a bit to say. I mean,
Well, I know nothing about network coding. Is that an applied area?
yeah, absolutely. Actually, about 2004 or 2003, I had a grant application for EPSERC, and they came back to me. No, it's not applied. You know, they were not so happy about that. And then next year, Microsoft Research started to look at network coding, and they came up with some file sharing system based on network code. Then I submitted the same application, but just wrote Microsoft is using it, and then lo and behold, then it got supported and everything. You know, so apparently it is network coding is definitely applied in various things. I mean, but it's still unclear to what extent it can be applied. I just got a PhD student on another grant called Network Coding Light, where we are basically trying to investigate to what extent this can be practical. But it's a big research area, it's exploding all the time. Lots of people worldwide are looking into this now, so I'm mostly interested in a bit more theoretical aspects of this research. So, and from a logician's point of view, there are lots of interesting questions you can ask. As soon as you allow yourself to ask this type of question, maybe some of them actually, a lot of these questions are not applied, but it allows you to understand the landscape in a different way than if you just do it from the purely applied perspective. From the applied perspective, it's very singular. You just sort of look at like one node. You can so to speak. You're basically just looking at very special type of formulas here. But if you go see from a logician's point of view, it allows you to take a bird's perspective and, so to speak, understand the theoretical landscape a bit better, I think. So this is what I want to work about here. And I'm by the way, here to the end of March. So, okay.
Any other comments? No. Okay, thank you once more.